All right, so this is the last section of Chapter 3. This will be Lecture 3, Part 5, the law of cosines. All right, so what is the law of cosines? Something that you cannot violate, otherwise you will be given a ticket, often called a point deduction. No, just kidding. Humor aside, what the law of cosines is, it's this. Consider this drawing of this triangle right here, shown in the illustration. And I've centered the vertex of angle A at the origin, and you see angles B and C. And B is the coordinates of, or the vertex for angle B is at C0. And I've labeled the side, the longest side is length A, and then we have side of length B, okay? And so if I drop a perpendicular from the vertex of angle C to the x-axis, you'll see I've created a right triangle, and it's, in effect, we have the height of this particular triangle. So in any triangle, the law of cosine stipulates this, that the length of a side, in this case A squared, is equal to the sum of the squares of the lengths of the other two sides, B squared plus C squared, minus 2 times the products of the other two sides, B and C, times the cosine of the angle between those two sides, okay? So you have three formulae. So basically, B squared is equal to A squared plus C squared minus the cosine of angle B, which is between A and C, and then times 2AC, of course, minus, okay, don't forget the minus sign, and then C squared is equal to A squared plus B squared minus 2AB cosine C, where C is the angle between A and B, okay? C is the angle between sides A and B, okay? All right, so how do we know this? Okay, so the coordinates of the vertex of angle C. What are the coordinates of the angle of vertex C right here? All right, so we know that the cosine of A is equal to the height. We'll call this the height of the triangle. So we'll call that the height of the triangle, divided by the length of the hypotenuse, which in this case is B. Okay, so so now we've got basically, okay, so we have H then is equal to B times the cosine of A. All right, and then we have the length of this segment, okay, we'll call that, say, K. And the sine of, let's see here, no, I'm sorry, what was that? What was I thinking? Cosine of A, no, I beg your pardon, that was the sine of A, sorry. The sine of A is, let's see here, have I got that backwards? Let's see, let me check again, that's not right. Let's check again. So, hold on, we have, let's call this H, and we call this K. All right, let's start from this vantage point. Sorry about that. We have basically a right triangle now. So we have A squared is equal to H squared plus C plus K squared. Okay. All right. This is C plus K. This is H. Okay, and it's a right triangle. So H squared plus C plus K quantity squared is A squared. All right, so now what is H? So if this is angle A, we know from previous work that the sine of angle A is equal to the sine of 180 degrees minus A, because angle A is in quadrant 2, right? The terminal side of angle A is in quadrant 2. So the reference angle, this would be the reference angle for angle A right here. You see, this is the reference angle, and so the sine of the reference angle is equal to the sine of angle A, because they're both in, because the sine is positive in quadrant 2. So so if we call this reference angle, say, yeah, so this right here is A bar. That's A bar, okay? And so the sine, okay, so H then is equal to, well, not H, that's not where I want it to go. I have the sine of A bar, the reference angle, is equal to opposite, which is H over B. So H is equal to B times the sine of the reference angle for angle A. But the sine of the reference angle, sine of reference angle A is just equal to the sine of angle A, because we're in quadrant 2. Remember, the sine of a quadrant 2 angle, of an angle which terminal side is in quadrant 2, is equal to the sine of its reference angle. Okay, so that's the H. Okay, so so we have, okay, and I'm not sure where the 0 comes from. Oh well, that's really not necessary. So that's your H squared. So this is your H squared. Now we need K plus C. Okay, so K plus C. All right, well, according to the illustration, K plus C. So what is K? So, okay, so let's figure out what that is. So K, so the reference angle for angle A is A bar. So we know that the cosine, okay, so the cosine of reference angle A would equal to K adjacent over B, the hypotenuse. But we also know, but we have to use the sine, because since we're in quadrant 2, the cosine of angle A is equal to minus the cosine of the reference angle, because we're in quadrant 2. Okay? So that means that, what? So in terms of the cosine of angle A, okay, we have the cosine, okay, the cosine of the reference angle, cosine of angle A is equal to the negative of cosine of angle A. So that means K must equal to B times the cosine of angle A with the minus sign. Okay, so K is equal to minus B times the cosine of angle A. So C plus K then becomes C minus B times the cosine of angle A. Okay, so now here, C plus K, this is actually, okay, and so since we're, so C plus K squared then, C plus K squared is equal to C minus B cosine of angle A, quantity squared. Now, when you square a difference, it doesn't matter how you perform the subtraction, okay? Because the negative 1 will always square away. So these two quantities are the same when you square a difference. So that means, okay, so here is an expression for C plus K. And so I'm doing it a little bit differently perhaps from the text, but we can go with this formula. All right, so now completing the square, so we have B squared cosine squared A minus what, 2BC cosine A plus C squared. So this trinomial is the square of here, and then b squared sine squared a. So now we see that b squared is a multiplier on cosine squared plus sine squared a. So we factor out a b squared minus 2bc times the cosine of a plus c squared. And of course, you know that cosine squared a plus sine squared a is just 1. So replace that with 1 and the result follows. Okay, so that is the proof of the law of cosines. It's not too difficult. So now we can solve a triangle using the law of cosines. So let's do that next. Let me paste something from the lecture notes. An example of solving a triangle. Okay, and this would be angle C right here. Okay, so given that angle A is, the measure of angle A is 46.5 degrees, as you see in the figure. The length of side B is 10.5. The length of side C is 18, as shown in the figure. We want to find the measure of angle B. Okay, so how do we know that B is 35.2 degrees? So the sine of B is B times the sine of A over A. So we have a case of the law of sines here, where the measure of angle B could be 35.2 degrees or 144.8 degrees. So in this case, we have to choose 35.2 because 144.8 plus 46.5 exceeds 180 degrees. So the largest angle in the triangle let's see, can we use 144? Yeah. Okay, so yeah, and so the largest angle in the triangle must be opposite the longest side, and so the longest side is C. So that means, yeah, so 35.2. Yeah, I'm not sure what's going on with this example. Let me check the text. This problem doesn't make any sense. Oh, okay, so they're finding the length of side A using the law of cosines. And then they find sine of B. Oh, I see what it is. Sine of B. Okay, so they use the law of sines to find the measure of angle B. Okay. Oh, I see. All right. Yeah. So yeah. So in any case, what happened was, suppose we don't know this, and let's see here. That's really a crazy problem. I don't think this problem is worded correctly. Oh well. Anyway, here's an example of, I would say for this particular example, just understand how to calculate the length of side A, knowing this information. Okay, that's all we really need to know. I think this problem is misspecified in the text. All right, so let's go on to some applications now. Let's talk about navigation problems. Give you some definitions for what's meant by heading and bearing in navigation type problems. So let me pull something from the notes. Give you some definitions here. Seem to have a lot of definitions in this class, don't we? All right, so let me paste it. All right, so for Heading and bearing. So what is bearing? All right, so here we have a coordinate axis, and we show the cardinal directions on the coordinate axis. So east, north, west, and south. Okay, so north is the positive y-axis, east is the positive x-axis, south is the negative y-axis, west is the negative x-axis. So we define what's called bearing, and it's the acute angle measured from due north or due south. So in this case, for this particular problem, the bearing is 30 degrees. The acute angle, okay, so you have this angle right here. Okay, so here you have a terminal side of an angle, and so the acute angle formed between this ray and due north is 30 degrees. Here in this case, if you have a ray like here, suppose that you're heading this way. Okay, suppose you're traveling on this trajectory with respect to the cardinal directions. So in this case, your bearing is 60 degrees. Here you have a bearing of 70 degrees. And so okay, I beg your pardon. I forgot to give you the notation. So a better way of looking at it, I see. I forgot to mention that. A better way of looking at it is say, okay, if this is the trajectory of, say, of a boat or an aircraft, all right, with respect to a coordinate system, this reference frame, north, south, east, and west, you say that you're bearing 30 degrees north, you're heading in the north direction, bearing 30 degrees east, okay? If your vector is in the first quadrant, okay? Now, if your vector is in the second quadrant, okay, and say you're on a trajectory, the acute angle is 60 degrees, your bearing is north 60 degrees in a westerly direction, okay? So you write it as north 60 degrees west. Now, in this example, if your trajectory is, if you're heading south in a westerly direction, your bearing is south 70 degrees west, okay? And in the fourth picture, you're heading south 50 degrees in the easterly direction, okay? So in bearing notation, always write north or south first, followed by the degree measure, followed by east or west, depending on which quadrant the vector is pointing in. So let's do an example. All right, so a pilot sets out from an airport and heads in the direction north 20 east, as shown in this illustration. So the airport will be here. Okay. After 1 hour, he makes a course correction and heads in the direction north 40 east, as shown here. Half an hour later, the pilot lands at point C, so that's later. The pilot lands at point C. All right, so the questions are, based on this illustration, we want to find how far has he traveled. Okay, so let's see here. Oh wait, let's see, in 1 hour, find the distance between the airport and its landing point and find the bearing from the airport to his landing. Okay, so we want to find the distance he's traveled. Okay, so here's the distance he's traveled. And we want to find this bearing right here. Okay, so here's how we can do that. So the length of AC we can find using the law of cosines. So let's see, he travels the first leg of his route 200 miles per hour at 1 hour. So this leg length will be 200. That's 200 miles. And then he makes a course correction, and so half an hour later, so he travels 50 miles. Let's see, is that right? No, half an hour, so he travels 100 miles in this direction. So he's traveling at constant speed. So in half an hour, 200 miles per hour, he travels 100 miles. And we know the measure of this angle. So what is the measure of this angle? We need to find the measure of that angle. So what can that angle be? So we have 20 degrees there. We have 90 degrees here. So this would be 70. This angle would be 70, so that would be 20. So the measure of this angle is 20. All right, let's see, or is that right? Yeah, so that would be 20 plus, and then the measure of this angle would be 50 degrees there. And then that would be 20 degrees there plus 90. Okay, so the measure of this big obtuse angle would be 160 degrees. Okay? So I would take that to be 160. That's 160. So that allows us to use the law of cosines to find the length of line AC, segment AC. So now we can find the length of segment AC. Because the way I found it was, this is 90, so that makes that angle 70. And then this is 90, so that makes that angle 20 degrees. And also, it's a transversal connecting two parallel lines. Okay. All right, so law of cosines, we have, let's call this distance x. Okay, so we will have x squared is equal to 200 squared plus 100 squared minus 2 times 200 times 100 times the cosine of the angle between 200 and 100, which is 160. And when you figure that out on your calculator, be sure it's in degree mode when you use your calculator, x would equal to 295.95 miles. Okay, and so now to find his bearing, well, its bearing is going to be north, degree measure east. So all we have to do is find the measure of this angle. Okay, so that means we'll probably have to use the law of sines. All right, so the sine, okay, so we'll call this A degrees, okay? So the sine of A degrees, which is what we want for the angle part of the bearing, over 100 is equal to the sine of 160 over x, okay? And we know x, so all we have to do is find the sine of A. So the sine of A is approximately equal to 0.11557. And if you punch inverse sine on your calculator, you'll find that A is equal to, the measure of angle A is equal to so many radians. So since we're in degree, no, so the inverse of the sine of this, if you're in degree mode, make sure your calculator's in degree mode, so that would be 6.36 degrees. So your bearing would be north, 6.636 degrees, east. Okay, so that's the answer to that problem. All right, interesting problem. So now the other problem is really a nice problem. And that is, we can calculate the area of a triangle if we know the length of the three sides, and that's called Heron's formula. So let me show you what Heron's formula gives. Okay, so it's a short, elegant proof for Heron's formula. Okay, so in this problem, we're given, we know A, B, and C, but we don't know the measures of the angles. We know the length of the sides of the three triangles. And it turns out that we can calculate the area of a triangle using this formula, the square root of s times s minus a times s minus b times s minus c, where we know A, B, and C, and s is 1/2 the sum of the lengths of the three sides, and it's called a semi-perimeter. All right, so this is a very powerful formula. And the proof, you can never do this in algebra. We know that the area of the triangle is equal to 1/2 AB times the sine of the angle between A and B. Okay, and if we were to square both sides, we would have A squared, area squared is equal to 1/4 A squared B squared times the sine squared of C. All right, and then we replace sine squared of C with its using the law of using the Pythagorean theorem. Sine squared of C, of course, is 1 minus cosine squared of C. And then we factor the difference of two squares. Okay? So, then we use the law of cosines to solve for the cosine of C. So, we know that C squared is equal to A squared plus B squared minus 2AB times the cosine of C. So we can solve for cosine of C. So so we have C squared minus A squared minus B squared all over 2AB is equal to the cosine of C. Negative 2AB, excuse me. Okay. All right, and so that's what we have here. So 1 plus the cosine of C is this expression. Add them together and simplify. And so 1 plus cosine C turns out to be this way. And then 1 minus cosine C is this expression. And then we just plug these two expressions in here. Okay, so we plug them in, and then we just basically simplify the entire expression. It's a big algebraic mess, needless to say. Well, it's not too big of a mess. And then we just replace, okay, then we know that this parameter right here, that's your semi-parameter. And then this parameter right here, I'll leave it to you to check. This should equal to S minus A. And then this would be S minus B. And then this would be S minus C. So you can check that algebraically. So Heron's formula, probably a WebAssign 2 question or two. No, I'm sorry, I got those backwards. This would be, sorry. This would be S minus C, sorry. S minus C. S minus C, S minus B, and that's S minus A. I'll leave that for you to check. Okay, and so you'll have probably a couple of WebAssign questions where you have to use this formula. All right, so let's solve a problem from geometry. We paste it in. All right, so in this case, a parallelogram has sides of lengths 3 and 5, and one angle is 50 degrees, okay, as shown in the figure. And we want to find the lengths of the diagonals. Okay, so suppose in this parallelogram A, B, C, I think that should be D. Make that D. Okay, so AB, we'll take AB to be CD, okay, all right, and then we'll take AD to be BC. Okay, so these will be 3. And then the measure of angle A is 50 degrees. Okay, so angle B, the measure of angle B, plus the measure of angle D is 360 minus 100, which is 260. So now why is that? Because this is a quadrilateral, and we know in a quadrilateral, the sum of the angles, sigma means sum, of a quadrilateral is 360. Okay, and by symmetry, That's 360. Okay, so that comes from geometry. And by symmetry, the measure of angle B is equal to the measure of angle D, so it's 130 degrees. So now all we have to do is find the lengths of the sides, so AC, okay, or the diagonals it is. So the diagonal AC would be equal to 3 squared plus 5 squared minus 2 times 3 times 5 times the cosine of angle B, which is 130 degrees. Keeping your calculator in degree mode in solving, you'll see that AC is equal to 7.3. And then you'll go turn around and use the law of cosines again to find the length of dB, which you'll discover to be 3.8. Okay, so use the law of cosines to find the lengths of the diagonals of a parallelogram. Again, there will probably be a WebAssign question regarding that. Okay, so now let's do a navigation problem. Let me paste it in. See if I can. Yeah, here we go. Wait 1 second while I copy it. Okay, so in this problem, 2 boats leave the same port at the same time. One travels at a speed of 30 miles per hour. Whoa, that's fast. At a speed of 30 miles per hour in a bearing of north 50 east. Okay, so that would be this boat right here. That's the vector, ripping along at 30 miles per hour. And the other travels at 26 miles per hour, traveling bearing south 70 east. Okay, so that would be this boat right here. How far apart are the 2 boats after 1 hour? Okay, so after 1 hour, this will be, say, the distance between the 2 boats as shown in green. So we want to measure that distance. So this is D. Okay, and after 1 hour, the boats, of course, this boat has traveled 30 miles. So 30 miles here. And the other boat has traveled 26 miles here. So the angle subtended by their direction, so we need this angle. So that would be 180 minus 75, minus 70 minus 50, so that's 60 degrees. So all you have to do is apply the law of cosines. So d squared is equal to 30 squared plus 26 squared minus 2 times 30 times 26 times the cosine of the subtending angle, which is 60, and you'll get 796. So take the square root of 796, and so after 1 hour, the boats are 28.2 miles apart. Okay. What power? Okay, so another one. Let's do another word problem. Civil engineering problem, perhaps. Let me paste it in. Bear with me. Okay, so in this problem, a 125-foot tower is located on the side of a mountain that is inclined 32 degrees to the horizontal. Okay, so the mountain is inclined 32 degrees to the horizontal. A guy wire is attached to the top of the tower and anchored at a point 55 feet downhill from the base of the tower, okay, shown in this figure. All right, so find the shortest length of the wire needed. Ah, okay, so let's see what we can do here. So we let x equal to the length of the wire, and what is the measure? So if we can find the measure of angle theta, then we can, of course, apply the law of cosines. So let's see here. what is theta? So can we use a transversal concept here? So let's see what can we do to get theta. So that's 32. So we know that the measure of this angle would be 180 minus 90 minus 32. So we'll call this alpha. So alpha is equal to 180 minus 32. No, gamma, I'm sorry. We'll call it gamma. 180 minus 32 minus 90. Okay, and so that would equal to 58 degrees. Okay, and then so theta, I'm taking would equal to 180 minus gamma, which is equal to 180 minus 58 degrees, and that would equal to 122 degrees. Okay, so just by extending the tower straight down, you'll form a right triangle, and then you can get the measure of this triangle formed with the hillside, and then find theta. Okay, so now it's just a matter of invoking the law of cosines. So we have x squared, the length of the guy wire, is equal to what? 55 squared plus 125 squared minus 2 times 55 times 125 times the cosine of 122. And so when you solve for x, take the positive value, and so x is equal to 161 feet. Make sure your calculators are in degree mode. Okay, so one more problem, and we're done with chapter 3. One more word problem. Another application of the law of cosines. Okay, so okay, so here we have the CN Tower in Toronto, Ontario, Canada, is the tallest freestanding structure in the world. Okay, so a woman on the observation deck, 1,150 feet above the ground, wants to determine the distance between two landmarks on the ground below, and observes that the angle formed by the lines of sight to the two landmarks is 43 degrees. Okay, so you see 43 degrees between the red and the blue. There's 43. She also observes that the angle between the vertical and the line of sight to one of the marks is 62 degrees. Okay, so 62 degrees is the line between the tower and this red line, and the other landmark is 54 degrees. So the angle between the tower and the blue line is 54 degrees. And so find the distance between the two landmarks. So we want to find that distance right there. Okay, so let's see, how can we proceed? So we want to find BC, the length of line segment BC. Now, okay, so here we go, and we proceed with calculating the cosine of 62 degrees. So that would be which triangle? All right, so let me erase this markup. All right, so we have cosine of 62 degrees would be, where is 62? So okay, so we have to have a right angle to calculate the cosine of 62 degrees. So it would be adjacent, which would be the height of the tower divided by the hypotenuse, which is AB. Okay, and so that's this formula. So solving for AB, we have 2450 feet. Now the cosine of 54 degrees, so let's see how we can calculate the cosine of 54. So that would be cosine of 54 degrees would be the height of the tower, okay, divided by the length of the hypotenuse, because this is 54 degrees right here. And so that would be AC. So it's 1956. So now we want this distance right here, BC. So we just use the law of cosines because we know AB, we know AC, and we know the length, measure of the angle between the two lines. So by the law of cosines, here it is stood up for you, and then we just solve for BC, which is 1,679 feet. Okay. All right. So now you must be nearing completion of all of your Chapter 3 web assign. Check the calendar on the class website for your test on Chapter 3. Okay, that should be coming up very soon. You have all the materials now you need for Chapter 3. Get with me during my office hour or send me an email if you have any questions about web assign or test preparation. And again, for your web assign questions, do not spend too much time solving each question. If you're spending more than 10 minutes on a question in web assign, ask for a hint, or if not the solution, okay? Because I want you guys to develop a habit of working really quickly on these problems. So speed counts here. Speed, accuracy, and knowledge. Okay, so Chapter 3 is in the books. So let's finish it off with good marks on our forthcoming test. Okay, so have a great day.